So in Unit 7, we're going to be looking at how we can apply everything that we've learned so far in this unit, at least to the first 4 units, kinematics, dynamics, work and energy, and impulse and momentum, to objects that are no longer just moving in a linear motion, in a linear sense, but are also rotating. So today we'll be looking at the rotational form of kinematics, which forms the basis for 7.1. So first we need to establish some conventions with rotational motion, okay? So there are 2 types of motion. There's translational and linear motion, which is motion when an object moves from one point to another. That's what we've looked at so far throughout this course. And then there's rotational motion, which is motion when an object rotates about a fixed point, like a tire rotating about its axle, okay? We can get a combination of these 2 types of motion, what we call rolling motion, which is a combination of translational and rotational motion. You roll by rotating from one place to another. So like a tire is going to rotate, let's say in this case this would be in the clockwise direction, and the tire will as a result move from left to right, okay? Represented by the linear velocity we see right here, okay? So rolling motion is a combination of translational and rotational motion. So the convention for direction in rotational motion is that counterclockwise motion is positive while clockwise rotation is negative, okay? So right here, the blue arrows are all pointing in a clockwise rotation, so this would be a negative rotation right here. Whereas if we were to move in the way that my pointer is moving right here in the counterclockwise direction, this would be a positive rotation, okay? So we'll look at now how we can convert from rotational to translational variables, okay? So radians is a unit used for angular displacement. So just as we have displacement from a position from one spot to another, we also have angular displacement from one angle, let's say where we're at with the spot A, to another angle, let's say where we're at with spot B. So theta or delta theta is what we use to represent our angular displacement, just as you may have seen trigonometry. And radians is the unit used for angular displacement. As you may be familiar with from trigonometry, radians is used for trig functions, okay? Angular velocity, which is represented by the letter omega, in the lowercase omega in this case looks like a little curly w, is the rate at which angular displacement occurs and has units of radians per second. And then lastly, angular acceleration, what we represent the letter alpha, okay, which looks like a little fish here, is the rate of change of angular velocity and has units of radians per second squared. All right. So we can see that the rotational analogs are very similar to their translational analogs of displacement, velocity, and acceleration, except now instead of considering objects that are moving from one spot to another, we're considering objects that are rotating. So in order to convert from, let's say, angular displacement to how far an object has traveled, okay, so which means translational displacement, okay, what we can take note of right here, okay, is that if a wheel rotates through an angle theta, the distance that is spanned right there is going to be, the distance spanned by the angle theta is going to be the distance or arc length of this particular segment of our circle right here, represented by the letter S, okay? So the arc length of this segment right here, okay, where we have a radius of r and angle of theta, is given by r times theta. The idea being is that, again from geometry, if we recall from geometry, for a certain segment like this, the angle theta is equal to the arc length divided by a radius. So the arc length is equal to the radius times our angular displacement, okay? And so this gives us right here, because our arc length is representative of the distance traveled, okay? If we can imagine that this was rolling on the ground, an angular displacement of theta would correspond to us rolling through a distance s, or displacement s. That means our translational displacement is x is equal to our arc length, so x is equal to r times theta. Okay, so this is our conversion from angular translational displacement. X equals r times theta. And then to convert from translational to angular, we just solve this equation by dividing both sides by r. So the same conversions follow for linear velocity / translational velocity and translational acceleration. So translational velocity is equal to the radius times the angular velocity, and translational acceleration is equal to radius times angular acceleration. The other unit that we have is a revolution. So one revolution is equal to the angular displacement that occurs after we've made, well, one full rotation. So one revolution is one rotation. And after we've made one rotation around a circle, we go through 2 pi radians, if we may remember from geometry. So one revolution is equal to 2 pi radians. So another useful conversion that we use to express angular displacement in rotational motion. So example 1, a bicycle has tires that are 0.8 meters in diameter. If the bicycle travels 30 meters over 4 seconds, what is 1, the angular displacement of the bike tire, and then 2, we'll look at the angular velocity of the bike tire. So in order to find the angular displacement, okay, what we need to do is we need to take, again, our equation that relates angular displacement to translational displacement, and we need to solve this equation for angular displacement theta, which is again going to be our arc length or translational displacement divided by the radius. So in this case, we have 30 radians divided by we're going to have 30 divided by 0.4. Since our diameter is 0.8, that means radius is 0.4, which gives us that our angular displacement is going to be 75 radians. Now 2 asks for the average angular velocity over this time interval. So again, angular velocity is going to be equal to our angular displacement divided by time. So we need to take the 75 radians and divide it by 4 seconds here, okay, in order to get 18.75 radians per second. The other way that we could do this is we could calculate our average velocity in terms of translational velocity, so 30 divided by 4, and then convert 30 divided by 4, which would be a little bit over 7, into angular velocity. So we could compute our average translational velocity first, and then convert that to our angular velocity. So either way is equally valid for this problem here. So rotational kinematics, okay? The rotational kinematic equations are angular velocity equals initial angular velocity plus acceleration times time. Angular displacement equals initial angular displacement plus angular velocity times time, plus 1/2 angular acceleration times time squared. And then lastly, we have angular velocity squared equals initial angular velocity squared plus 2 times our acceleration times our displacement minus our initial displacement, angular displacement. If these look familiar to you, that's because they are word for word, or better said, variable for variable, the translational kinematic equations, except with the translational variable swapped out for the rotational variables. So final velocity is replaced with final angular velocity, final position is replaced with final angular position, so on and so forth. These first 2 equations right here are on your equation sheet. This third equation right here is not on your equation sheet. However, you don't really have to memorize it because it's the same thing as the other, as a translational kinematic equation, which is on your equation sheet. It's just that it has the translational variables swapped out for their rotational analogs. And lastly, we take a look at interpreting motion graphs for rotational motion. Okay, so the same principles that apply for motion graphs for translational motion also apply for motion graphs for rotational motion. Okay, so for example, if we're given a graph of angular displacement versus time, okay, the angular velocity is going to be equal to your angular displacement divided by time, which is going to be the slope of your tangent line to the angular velocity angular position versus time graph. Similarly, for an angular velocity versus time graph, the slope of the angular velocity versus time graph is going to give us angular acceleration, as angular acceleration equals change in angular velocity over change in time. Just the same way as the slope of translational velocity versus time graph gave us the translational acceleration. All right. And then now if we move to area beneath the curve, the area, again, the same way the area beneath the curve of a translational velocity versus time graph gives us the translational displacement, the area beneath the curve of a angular velocity versus time graph gives us the angular displacement, and then the area beneath an acceleration versus time graph gives us the change in angular velocity, just as the area beneath a translational acceleration versus time graph gives us the change in translational velocity. So all of our key principles from translational kinematics also we can see hold for rotational kinematics. So let's take a look at an example problem real quick. with rotational kinematics. A rotating wheel requires 3 seconds to rotate 37 revolutions. Its initial angular velocity at the beginning of the 3-second interval is 21 radians per second. What is the constant angular acceleration of the wheel? So the first thing we need to take note of is writing down our knowns and unknowns. Again, in this case, we know that our time is 3 seconds. We know our initial angular displacement or angular position is 0 radians, just the same way that we can say our initial translational position is 0 meters. And then we know that our initial angular velocity at the beginning of the 3-second interval is 21 radians per second. Now, the rotating wheel goes through 37 revolutions, which gives us our final position. Again, revolutions is going to tell us how far, and there's a parentheses around that, we travel in terms of an angle. So 37 revolutions is going to refer to our final position. However, the only thing is we have to work in radians, so we need to convert 37 revolutions to radians. So we take note of the fact that in one revolution, there's 2 pi radians. So we do a unit conversion where we convert from 37 revolutions to radians. So we multiply 37 by 2 pi, the revolutions cross out and leave us with rad, which gives us 232.5 radians. So our final angular position is 232.5 radians. Lastly, our angular acceleration is our unknown. That's what the problem asks us to find for right here. Okay, so we identified that the equation we need is final angular position equals initial angular position plus initial angular velocity times time plus 1/2 angular acceleration times time squared. Man, that's a mouthful. All right, so we're going to get 232.5 radians equals 21 radians per second times 3 seconds plus 1/2 of the angular acceleration times 3 seconds squared. So as a result, we're going to get 169.5 radians equals 4.5 seconds squared times our angular acceleration. I just took the 21 times 3 and I subtract it from both sides to get 169.5. And then we divide both sides by 4.5 seconds squared in order to get our angular acceleration, which comes out to be 37.6 radians per second squared. And thus is an example problem with rotational kinematics.